In this video over section 4.3, linear independence, we're going to take a look at the concept of linear independence that we learned a while ago, but in a more abstract setting for general vector spaces. Let's get straight to the definition, and then we'll work through some examples where we figure out a little bit about what the definition means. So a set of vectors, we'll call them v1, v2, up through vm, in some general vector space V, is called linearly dependent if there are scalars, c1, c2, up through cm, so there's just as many scalars as there are vectors, not all of them zero, such that this equation holds. So on the left here, we have a linear combination of the set of vectors, like we learned about in the previous section, but now we have this linear combination set equal to 0. Otherwise, so if this does not work out, the set is called linearly independent. So what that means is a set is linearly independent if this equation forces each of the scalars, the coefficients, to all be 0. Now let's try out this definition. Let's determine if this set of two vectors x plus 2 and 2x plus 1 is linearly independent. In this example, we're looking at polynomials, and we can think about this as the subspace of polynomials P1, or we could think about this as just a set of functions. It doesn't really matter when we're considering linear independence, because all we're going to look at is a single equation. So I've set up a linear combination of the two vectors, the two polynomials, and I've set it equal to 0. And this mirrors the equation from the definition. So what we have to do to determine if this set of vectors is linearly independent is see what solutions, what values of c1 and c2 work in this equation. So what's going to happen is that this vector equation, this polynomial equation, let's say, is going to lead to a system of linear equations that we get by comparing the coefficients on the left side with the coefficients on the right side. So what I mean is that the coefficient on x has to match the coefficient of x over here. That's so 0 has to match 1 and 2 over here, or 1 times c1 plus 2 times c2. And then the constant coefficient, the 2 times c2 and a 1 times c2, also has to be 0. So that gives us a system of two equations in two variables that we know how to solve using Gauss-Jordan elimination. So I've translated my system of linear equations into an augmented matrix, and then I'm going to use row reduction to find the answer to this system. So what have I done here? I've multiplied row 1 by 2, and I've subtracted it from row 2 to eliminate this 0, and then I left off a couple steps, but what I did was I divided through by -3 to create a 1 in this position, and then I used that 1 to eliminate the 2 to create this matrix in reduced row echelon form. And what this final form tells us is that the only solution is c1 equals 0 and c2 equals 0. And since that is the only solution to the original equation, 0 and 0, that means that this set of two polynomials is linearly independent. Let's do one more example. just using this definition, I want to determine if this set of three vectors is linearly independent. So what I've done is I've taken the two vectors from the previous example, and I've thrown in an extra one, x plus 1. And the process is almost identical. We need to look at this equation, so a linear combination of the three vectors, three polynomials, set equal to 0. And this is going to lead to a system of two equations, because the coefficient on the x's has to be 0, and then the constant coefficient from the left has to also be 0. So we get these two equations, c1 plus 2c2 plus c3 equals 0, and then 2c1 plus c2 plus c3 equals 0. So we do the usual process. We translate our system of linear equations into an augmented matrix, and then we go through the steps of row reduction. And we'll go over this a little bit. Again, multiply by 2 and subtract from row 2 to get this augmented matrix. And then you can divide through by 3, and then you get a 0, 1, 1/3, and 0 on the bottom row. And then use this bottom row to eliminate that 2. So we multiply row 2 by 2 and subtract it from row 1 to get this. So what this tells us, since there's only 2 pivot positions in our matrix with 3 variables, that tells us that there's going to be many solutions to the system of equations. So that means that there's going to be some solution where or at least one of our coefficients from the original equation is not 0. So the set that we started with is linearly dependent.